Testing, can you hear me? Testing, can you hear me? Okay, one last test. So my stream got disconnected last time, so I'm just going to continue from where I last left off. Uh, yeah, so I was reading this example. I was reading about an example of basic operation. So here they have a function about sorting an array. So current largest index 0, and for from index 1 to for all the way till the rest of the size, if the element has, like if the current largest one, if the element in the current largest position is smaller than the current element, then the current largest is set to the new index. Okay. The most important factor affecting the running time is normally the size of the input. For a given size n, we often express the time t to run the algorithm as a function of n written as tn. We always assume tn is a non-negative number. Let us call c the amount of time required to compare two integers in a function in function largest. We do not care right now what the precise value of c might be, nor are we concerned with the time required to increment variable I, because this must be done for each value in the array, or the time for the actual assignment when the a larger value is found, or little bit of extra time taken to initialize current large. We just want a reasonable assumption. Reasonable approximation for the time taken to execute the algorithm. The total time to run largest is therefore approximately Cn, because we must make n comparisons, with each comparison costing C time. We say that the function largest has a running time expressed by the equation Tn is equal to Cn. And this isn't true because you're also comparing size and you're also incrementing I. And then you're comparing this. Assigning, comparing again, and then possibly assigning. It should be 2C, not 1C, because there are two comparisons. They said they're not concerned with the time required to increment a variable I, because this must be done for each value in the array. So, or the time for the actual assignment when a larger value is found or the little bit of extra time to initialize current larger. I don't get this point. That is cause even the amount of time necessary to copy an integer, no matter how large an array or in a typical computer, the time to copy the value from the first position of the array is always C1. Thus, the equation for this algorithm is simply Tn is C1, indicating that the size of the input n has no effect on the running time. This is called a constant running time. The growth rate for an algorithm is the rate at which the cost of an algorithm grows as the size of its input grows. The following figure shows a graph of 6 equations, each meant to describe the running time for a particular program or algorithm. A variety of growth rates that are representative of typical algorithms are shown. We have n factorial. We have 2 to the power of n. We have 2n squared. Five n log 2n. We have 20n, 10n. Okay. Oh, what is this? Why is this slower? 20n. Oh, it's zoomed in over here. The two equations labeled 10n and 20n are graphed by straight lines. A growth rate of Cn is often referred to as a linear growth rate or running time. This means that as the value of n grows, the growth rate, the running time of an algorithm grows in the same proportion. Doubling the value of n roughly doubles the running time. An algorithm whose running time equation has the highest order term containing a factor n squared is said to have a quadratic growth rate. So we have linear growth rate, which is this line and this line. So this line and this line, and then we have a quadratic growth rate. We have a logarithmic growth rate. No, this is not logarithmic. I think if you remove the 5n, then we have a logarithmic growth rate. This is an exponential growth rate. This is a factorial growth rate, and factorial is the worst, right? As you can see from the figure, the difference between an algorithm whose the line labeled n factorial also grows exponentially. Isn't there any word called factorially? An algorithm whose running time has cost 10n and another with cost 2n squared becomes tremendous as n grows. For n greater than 5, the algorithm with the running time 2n squared is already much slower. This despite the fact that 10n has a greater constant factor than 2n squared. 10 squared, 2n squared. Graph also shows that the equation 5n log n grows somewhat more quickly than both 10n and 20n, but not nearly so quickly as the equation 2n squared. For constants a, b greater than 1, n is equal to a grows faster than either log a n or log n to the power of b. They made a mistake here. They mean b as a base. Finally, algorithms whose cost t n n to the power of 2 or n factorial are prohibitively expensive, but even modest values of n. Note that for constants a b more than 1, a to the power of n grows faster than a n to the power of b. We can get some further insight into relative growth rates for various algorithms from the following table. Most of the growth rates that appeared in typical algorithms are shown, along with some representative input sizes. Once again, we have seen that the growth rate has tremendous effect on the resources consumed by an algorithm. Assume all logs are base 2. You're given this set of growth functions. For the growth function to the power of n, type a value for which this function is most efficient of the six. There's no integer, type none. So when n is 0, okay, when n is 1, we have 1, 1. No, this is not the most efficient. So none is the answer, right? What? Is it 1? Check answer. Tap a value for which this function is the most efficient of the six. 1, 1. If I do 2 factorial, how about, okay, let's see the graph. 2 to the power of n, when it is 5, when the input size is 5, we have 5 factorial, which is very large. 2 to the power of 5 is smaller. 5 times 10. Okay, let's try 5. For the growth function, 5n log n, type of value. Okay, let's see. This one, then I guess it's none. What? 5n log n. One, two. Really? 1? 5, 1. I don't, hold on a minute. F of n, 5n log 2 n, and let's do f of, why does it go to minus? Log base 2n. Is this graph drawn wrong? 1 is 0. How do I insert a table? Okay, let's compare 5 with 2 to the power of n. No, 2 to the power of n is smaller. No, it's not. 1 factorial. Yeah. For the growth function to the power of n type of value for which this function is the most efficient of the six, there is no integer value for which it is more efficient, type none. 2 to the power of n. Oh, I already did this. 5. We rank them. Okay. Ascending order of growth rates. N to the power of 4 grows larger than the power of 4 over 3, right? N squared 2n. I think 2n square will grow the largest, right? Or maybe not. Why is there a 2 on top and no 2 over here? Log. This will be the smallest. Constant terms never matter, so ignore them, like multiplying 9. So 9 and 5 does not matter. This 2 over here bothers. Maybe this goes here. This goes here. Oh, so this grows much. How would I? Is there a way to know? Is it the same? No, it's not the same. Root n log. Let's put this here. Let's put 4 here. 4 over 3 is definitely smaller than this. N square is definitely smaller. And then 2 to the power of root n is, this will eventually grow bigger, right? Like this part will eventually grow bigger. Let's check. Something is missing. Maybe this? No, that doesn't make sense. Log should be much smaller. Focus on the I did focus on the exponents. Is this the issue? 2 to the power of root n? Generally, things that are only logs go first. That log grows slower than log n. Constant powers of n comes after things with only log factors. Even small constant powers of n. So root n grows faster than log 3n. What's wrong with what I wrote? Generally, things with some function n in the exponents go last. These are called exponentials. Of the exponentials, you see what has the biggest function in the exponent. Example says root n grows faster than log n, then 2 root n grows faster than 2 log n. Okay, let's try. G of n to square root n n to the power of h n to the power of n square. Oh, n square grows bigger. N square grows bigger. Root n this, then this. I'm right. 5 log n g of x h of x f n 5 log base 2 log base 2 n. This goes here. I don't get what the issue is. 5 log n root n log n and then 2 root n square n 4/3. Oh, 4/3 is smaller. N square. So wait, n to the power of 4 should be the biggest, right? So this function is the biggest. Then comes n square. Then comes this. Hold on, maybe not. No. Then comes this. Then comes this. 2 and 4/3, and then we have n log n. To the power of 4, to the power of 2, 2 root n, this first, and then 4 to the 4/3. Two root n and then the 4/3. How do I check the answer though? No, I mean get the correct answer. While analyzing an algorithm, should we study the best, worst, or average case? Normally, we are not interested in the best case because this might happen only rarely or generally is too optimistic for a fair characteristic of an algorithm's running time. In other words, analysis based on the best case is not likely to be representative of the behavior of the algorithm. However, there are rare instances where a best case analysis is useful, in particular when the best case has a high probability of occurring. The shell sort and quick sort algorithms both can take advantage of the best case running time of insertion sort to become more efficient. They're going to teach sorting later, right? Binary trees, yeah, they would teach sorting later. How about the worst case? The advantage to analyzing the worst case is that you know for certain that the algorithm must perform at least that well. This is especially important for real-time applications, such as for the computers that monitor an air traffic control system. Here, it would not be acceptable for an algorithm that can handle n airplanes quickly enough most of the time. Alright, let's go to the next chapter. Imagine that you have a problem to solve and you know of an algorithm whose running time is proportional to n square, where n is a measure of the input size. Unfortunately, the resulting program takes 10 times too long to run. If you replace your current computer with a new one that is 10 times faster, will the n square algorithm be acceptable? If the problem size remains the same, then perhaps faster computer will allow you to get your work done quickly enough even when an algorithm having a high growth rate. But a funny thing happens to most people who get a faster computer. They don't run the same problem faster, they run a bigger problem. Say that on your old computer you were content to sort 1000 records because that could be done by the computer during your lunch break. On your new computer, you might hope to sort 100,000 records in the same time. You won't be back from your lunch any sooner, so you better off solving a larger problem. Because the new machine is 10 times faster, you would like sort 10 times as many records. If your algorithm's growth rate is linear, then 100,000 records on a new machine will be sorted in the same time as 10,000 records on the same machine. If the algorithm's growth rate is greater than Cn, such as C1n square, then you will not be able to do a problem 10 times the size in the same amount of time on a machine that is 10 times faster. How much larger a problem can be solved in a given amount of time by a faster computer? Assume that the new machine is 10 times faster than the old. Say that the old machine could solve a problem of size n in an hour. What is the largest problem that the new machine can solve in 1 hour? The increase in problem size that can be run in a fixed period of time on a computer that is 10 times faster. Change 10, 10. So n before, n new. And the factor of change in speed. So old versus new. 10, 10, 7.37, 3.16. This table illustrates many important points. The first two equations are both linear. Only the value of the constant factor has changed. Okay. Linear constant factor. Wait, I don't understand if and the first column lists the right-hand sides of the right-hand sides for 5 growth rate equations. Or this is the growth rate. This is the actual n. This is the new n. Okay, now I understand. Both cases, the machine that is 10 times faster gives an increase in problem size by a factor of 10. In other words, while the value of the constant does not affect the absolute size of the problem that can be solved in a fixed amount of time, it does not affect the improvement in problem size gained by a faster computer. This relationship holds true regardless of the algorithm's growth rate. Constant factors never affect the relative improvement gained by a faster computer. Oh. An algorithm with time equation 2n squared does not receive nearly as great an improvement from the faster machine as an algorithm with linear growth rate. Instead of an improvement by a factor of 10, the improvement is only square root of that. Thus, the algorithm with high growth rate only solves a smaller problem in a given time in the first place. It also receives less of a speedup from a faster computer. As computers get even faster, the disparity in problem sizes becomes even greater. Now that something special happens in the case of the algorithm whose running time grows exponentially. If we look at its plot on the graph, the curve for the algorithm whose time is proportional to the power of n goes up very quickly as n grows. The increase in problem size on a machine 10 times as fast is about n plus 3. To be precise, it is n plus log 10 base 2. The increase in problem size for an algorithm exponential growth rate is by constant addition, not by a multiplicative factor. Because the old value of n was 13, the new problem size is 16. If next year you buy another computer 10 times faster yet, then the new computer will only run a problem of size 90. If you had a second program whose growth rate is 2 to the power of n, and for which the original computer could run a problem size 1000 in an hour, then a machine 10 times faster can run a problem only of size 1003 in an hour. Thus, an exponential growth rate is radically different than the other growth rates shown in the table. The significance of this difference is an important topic in computational complexity theory. When you do buy a faster computer, an algorithm with a slower growth rate provides a greater benefit in terms of larger problem size that can run in a certain time on a new computer. Okay, I'll just go to the next chapter. Did they? Okay. This is asymptotic analysis. Despite the larger constant for greater curve for the curve labeled 10 n in the figure above, 2n squared crosses it at a relatively small value of n is equal to 5. What if we double the value of the constant in front of the linear equation? As shown in the graph, 20n is surprised by 2n squared once n is equal to 10. The additional factor of 2 for the linear growth rate does not much matter. It only doubles the x-coordinate for the intersection point. In general, changes to a constant factor in either equation only shift where the two curves cross, not whether the two only shifts where the two curves cross, not whether the two curves cross. So this intersection point will get larger and larger and larger and larger if we increase 20n to 30n, 40n, 50 and so on. So this constant times n will still be slower on the long run. When you buy a faster computer or a faster compiler, the new problem size that can be run in a given amount of time for a given growth rate is larger by the same factor, regardless of the constant on the running time equation. And time curves for the two algorithms with different growth rates still cross, regardless of their running time equations constants. For these reasons, we usually ignore the constants when we want to estimate the growth rate. When you want an estimate of the growth rate for the running time or other resource requirement of an algorithm. This simplifies the analysis and keeps us thinking about the most important aspect, the growth rate. This is called asymptotic algorithm analysis. To be precise, asymptotic analysis refers to the study of an algorithm as the input size gets big or reaches a limit. However, it has proved to be so useful to ignore all constant factors. The asymptotic analysis is used for most algorithm comparisons. In rare situations, it is not reasonable to ignore the constants. In comparing algorithms meant to run on small values of n, the constants can have a large effect. For example, if the I don't need an example. So small values in very large values, it doesn't matter. But in small values, it would, right? Asymptote analysis is the form of back of the envelope estimation for algorithm resource consumption. It provides a simplified model of the running time or other resource needs of an algorithm. Several terms are used to describe the running time equation of an algorithm. These terms and their associated symbols indicate precisely what aspect of the algorithm's behavior is being described. One is the upper bound. For the growth rate of the algorithm's running time, it indicates the upper and highest growth rate that the algorithm can have. Because the phrase because the phrase has an upper bound to its growth rate of fn is long and often used when discussing algorithms, we adopt a special notation called big O. If an upper bound of an algorithm's growth rate for, say, the worst case is fn, then we would write that this algorithm is in the set OFN in the worst case, or just in OFN in the worst case. Example, if n square grows as fast as tn, for the worst case, we say the algorithm is in ON square in the worst case. The following is a precise definition for an upper bound. Tn represents the true running time of an algorithm. Fn is some expression for the upper bound. For Tn, a non-negative valued function, Tn is in set OFN if there exist two positive constants, C and N naught, such that Tn is less than or equal to C times Fn for all n greater than N naught. This definition is confusing, but I know what they mean. So if we have T and that grows like this, and we have Fn, well, Fn is greater than Tn after N naught, or I should say when n is greater than N naught, then Tn is in set OFN, right? Is in set OFN. Is in set OFN. Let's do Gn, and then we have N1. Is also in set OGN. Because they exist, because Gn is like more than Tn after some point. It doesn't have to be greater all the way, it has to be greater after some cutoff point. And we multiply it by a constant as well. So I think C times Gn would not matter. There has to be some constant. If we have, let's erase these two lines and let's the comparison line. Let's draw it like this. And let's do like h of n. But then c times h of n would bring this up above, right? Yeah. If we have a straight line, can I draw a straight line? Or I can't. So this. Uh-huh. And the comparison line, I will draw same gradient. Or I should draw it like this. T N F N T N in set O F N. Hold on. I should take O n function. I should make this a straight line as well. Because Tn is more than Tn becomes less than, right? Did I type more than before? Yeah. Comes, I should try. Cause there exists C such that Tfn becomes more than Tn. There exists a value of C such that if you make this steepen up, it becomes more than Tn. And if this does not cross the origin, this is steeper and it does not cross the origin, then there also exists Cn and n naught such that this is true after for n greater than n naught there. Like after some cutoff point, we are allowed to use a constant function to make the functions steeper. After some cutoff point, this function will become more than Tn for all n. So constant C, same for this. H of n. Now you may be wondering that I can always write a C that makes h of n bigger. For example, if h of n is log n. Let's remove this. Okay, if I have root n log n, and I have g of n is equal to n over 2. Yeah. After some cutoff point, g of n is always smaller, but you may be wondering that I can just multiply this by some constant, that I can do this with any function. I can just multiply them with a constant. They'll be bigger, but the thing is they won't be bigger for all n. N over 2 still surpasses this function. G of n still surpasses f of n no matter what constant I multiply with. No matter what constant I multiply f of n with. So f of n cannot be used as a worst time thingy. We have what can be used as a worst time approximation. What can be used as big O is simply n. So O of n. The worst time complexity is O of n. Consider the sequential search algorithm for finding a specified value in an array of integers. Visiting or examining one value in the array requires CS steps, where CS is a positive number, and if the value we search for has equal probability of appearing in any position in the array, then in the average case, Tn is equal to CS n over 2. By the definition, Tn is an On, for n naught is equal to 1 and C is equal to CS. For a particular algorithm, Tn is equal to C1n square plus C2n is the average case where C1 and C2 are positive numbers. Then we have C1n square plus C2n less than equal to C1n square plus C2n square. Just less than C1 plus C2n square. So this function is an On square because this is less than this. Constant values will have O1 at upper bound. Constant values, if I have a constant value of some algorithm that takes constant time, this is called O1 running time, because there can always be a function that I can multiply by a constant and go above this. If Fn is an OGn and Gn is an OHn, then Fn is an OHn. Okay. If Fn is an OKGn and for any constant k more than 0, then Fn is an OGn. If F1 is an OG1 and F2 is an OG2, then we add them, then the sum of them is an O max G1, G2. And then multiplying them gives, we multiply the O notation. A mistake that people often make is to confuse the upper bound and the worst case. The upper bound of an algorithm indicates the upper or highest growth rate that an algorithm can have for a problem of size n. Upper bound is like, it's like the graph above Tn, which it cannot surpass. Any graph. So both f of n and g of n are are in big O. The sequential search algorithm accepts as its input an array of n keys and the target key k to search for. The upper bound of sequential search algorithm. Do you think this is the correct way to ask this question? With 3 inputs, when the target k key is located at the first position, when the target k key is located at the last position, the average cost over all possible positions. The best case, only a single element is visited, so Tn is 1. Accordingly, an upper bound for the algorithm is the best case O1. Even when n increases, the cost of the best case does not grow. In the worst case, n elements must be visited, so we have Tnn. So an upper bound for the algorithm in the worst case is On. No matter what the value of n, for some constancy, Cn is bigger than n. Average case for the algorithm about n over 2. So this is also On. This is also On. Each of these is the best upper bound for the growth. Best upper bound. Not this, because 5n plus 3 will surpass log n no matter what constant is multiplied by. So it's this, right? Or maybe this. Yes. N log n. N log n. Okay, it grows really quickly. Yeah, it's like, so it's like On, but multiplied by some. Yeah, that's correct. So isn't sequential search false? No, yeah, that's true. This is bigger than the, yeah, best upper bound in log n. Then only 2 questions. Lower bound and theta notation. Okay, this is going to take a long time. Big O notation describes the upper bound. In other words, big O notation states a claim about the greatest amount of some resource that is required by an algorithm for some class of inputs of size n. Similar notation is used to describe the least amount of a resource that an algorithm needs for some class of input. Like big O notation, this is a measure of the algorithm's growth rate. Like big O, it works for any resource, but we must often measure the least amount of time required. And again, like big O, we are measuring the resource required for a particular class of inputs, the worst, the average, or best. The lower bound for an algorithm is denoted by big omega. So we have big O and we have big omega. For Tn, a non-negatively valued function, Tn is in set omega Gn if there exists two positive constants C and n naught such that the algorithm will be bigger than Gn no matter the constant for some constant for all n greater than or equal to n naught. Okay, so this over here is the omega n, is the omega for this. So that's the opposite case. Theta notation, the definition of big O in omega gives us a way to describe the upper bound and the lower bound. When upper bound and lower bound are the same within a constant factor, we indicate this by using theta notation. The algorithm is said to be theta hn if it is in h o hn and it is in omega hn. Note that we drop the word in for theta notation because this is strict equality for the two equations with the same theta. In other words, if f is theta and g is, we say it is, on, and in omega n in the average case, we say it is theta n in the average case. Given an algebraic equation describing